K is the dimension of the column space of A. Call A or what? No. 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 It is not N. It is the number of pivot columns, so you can write that, yeah. No, because I had the word dimension, so that won't work. Yeah. Row space of A or row space of A transpose, because that is the column space, yeah. So any of those are correct, yeah. If A is m by n, what the rank of A plus the dimension of the null space of A is n. Good. Right, so the rank is the column space, which is the number of pivot columns. The dimension of the null space we talked about last class being the number of free variables. If you add the number of pivot columns and the number of free columns, you get the total number of columns. N. All right, true or false, the row space of A equals the column space of A transpose. True. Okay, the row space of a matrix, which we call the row, we denote row A, is a set of all linear combinations of the rows of A. So think of the rows as vectors where we just write them horizontally instead of vertically. Okay. Each row of A has n entries, right? Because there are n columns, so there should be n entries in each row. So the row space is a subspace of Rn. Okay. So the row space lives over here in Rn. Okay, so if you think of A as the standard matrix of a linear transformation, Rn is the domain, Rm is the codomain, the row space lives in the domain. Okay, the row space is the same thing as the column space of A transpose, because when you transpose a matrix, that just means make the columns rows and make the rows columns, so the row space is just the column space of A transpose. And if A is an m by n matrix, this is just sort of a handy picture to like think about where all these things live. Yeah. So the null space, remember, is the set of all things in the domain that get mapped to 0. So 0 will always get mapped to 0, so I have 0 in the null space. It's also in the row space because you can take linear combinations where all your weights are 0 and you'll get 0. All right, and then the range of your transformation T is your column space, right? Because your column space is all linear combinations of your rows, and it's also your row space of A transpose. And then your null of A transpose also lives in Rm. Okay, so we've got a theorem that if two matrices A and B are row equivalent, then their row spaces are the same. Okay, so if B is an echelon form, the non-zero rows of B form a basis for the row space of A, and they form a basis for the row space of B. So in practice, this theorem is used to find a basis for the row space of A. You row reduce A to a matrix B in echelon form, use the non-zero rows of B to form a basis for row A. All right, we had talked about the definition of rank in our quiz. The rank of a matrix A is just the dimension of the column space of A, which is the number of vectors in the basis for the column space, or also the number of pivots when you row reduce. The rank theorem basically comes down to this. The rank of A plus the dimension of the null space of A is the total number of columns. Again, we talked about that in the quiz. And then based on these new definitions, we can add a few things to the invertible matrix theorem, which is that like really long list where if one thing is true, they're all true. If one thing is false, they're all false. And so we can say the columns of A form a basis for Rn. So that means that there's a pivot in every column, right? If you form a, then they have to be a basis, they have to be linearly independent and span Rn, right? So if they form a basis, then both of those other things are true and everything else in the list is true. The column space of A is all of Rn. So the columns of A are spanning Rn. That was already part of the invertible matrix theorem. So it's just another way of saying that. For spanning, column space of A being, this would be a pivot in every row. Yep. The dimension of the column space is n. That means you have n pivots. Again, n pivots was already in our list of invertible matrix theorem statements. The rank of A is n. Same thing. The rank is the dimension of the column space. So these two are like identical. The null space of A is just the zero vector, right? So that means that when you solve AX equals 0, you get only the trivial solution because the null space is the set of things. Yeah, so there's no free variables, right? That was already in our list of invertible matrix theorem statements. We're just stating it a different way now. And the dimension of the null space is 0 because we said the dimension of a space that only contains a 0 vector we defined to be 0. All right. The dimension of null A is 1, is 0 because we taught in the last class, it was very briefly, but I mentioned that if 0 is the only vector in your vector space, we say that its dimension is 0, right? To differentiate it from a vector space that has a one single non-zero vector as its basis. Yeah. Okay, so here's our picture again. Let's look at some examples. All right, so I have 3 row equivalent matrices. These are all row reduced versions of each other. Okay. So I want to give an example of a vector in the column space of A. Any vector in the column space of A. 1, 0, 3, negative 3, right? The column space of a matrix is the set of all linear combinations of the columns. So you picked one column from the matrix A because you could put a weight of 1 on that first column, 0 on every other column. So 1, 0, 3, negative 3. It doesn't even have to be. Yeah, to be in the column space, because I'm not asking for a vector in the basis for col A, just any vector in col A. Yeah. So this is an element of col A. All right, how about the row space of A? I want any vector in the row space of A.
1, 2, 0.
Yep, I could pick any row from A, right? Because the row space is just the all the linear combinations of the rows of A. And think of the rows of A as vectors. They're just written horizontally. And if that like twists your brain up, you can rewrite it vertically if you want, right? So you can do 1, 2, 0, negative 1, negative 4, negative 2, 0. Yep. Yep, the row space of A is the column space of A transpose. All right, and a vector in the null space of A. So remember, the null space is a set of all vectors that get mapped to the 0 vector, or the set of all solutions to AX equals 0. Nice. The 0 vector is always in the null space. So we don't even have to do any work to find a vector in the null space. 0 is always in there. But how many zeros should I put in it? 7. 7. Because, yeah, it's what do I have to multiply A by, right, to get 0, 0, 0, 0, right? Because you have to be able to take your row and multiply it times your column. So you're going to have 7 entries. So the 0 vector with 7 entries. I don't know. I don't think so, because I have this in row reduced form. If I augmented with zeros, I have free variables, so it would not be the only solution. Yeah. There are other vectors in the null space, for sure. Okay, so based on our three matrices here, what's the rank of A? How do you know that? The number of pivot columns, yeah. So the rank of A is the dimension of the column space, which is the number of pivot columns. So 3. Okay. And then what's the dimension of the null space of A? 4, because your rank and the dimension of your null space have to add up to 7, the total number of columns in this case. So this has got to be 4. What's the dimension of the column space? 3. Dimension of the column space is the definition of rank. Yep. And what's the dimension of the row space? It's 3. It's also an alternate definition of rank. The rank of A is the dimension of the column space or the dimension of the row space. The dimension of the column space and the row space are always the same. There are 4 rows, yeah, but there's only three vectors in a basis for the row space. Because the 4 rows of A are not linearly independent. You can get rid of one and still have a basis. Okay. Okay, column space of A is a subspace of, right? Where does it live? Column space of A. No. Like what dimension does it live in? How many entries are in each element of the column space? 4, yeah. Because the column space is the set of all linear combinations, right? So look at, I picked a vector in the column space. It's 1, 0, 3, -3, right? It's got 4 entries. So column space is definitely a subspace of R4, right? All the vectors in there live in R4. Might not be all of R4, but all the vectors are in R4. Okay. The null space of A is a subspace of R7, yeah. So I picked a vector in the null space up here. It had 7 entries. So the null of A is a subspace of R7. Row space of A, subspace of R7. Look at the vector we picked from row A, right? It lives in R7. Column space of A transpose. The dimension of the column space of A transpose is the rank. But I want to know, where do the elements of the column space of A transpose live? R7, yeah. Because the column space of A transpose is the same thing as the row space of A, right? So this is R7. Okay. The null space of A transpose, R4. And the row space of A transpose, that would be the column space of A, which is R4. Good. All right, can we move on? We ready? Okay. All right, so I want to find a basis for the column space of A, the row space of A, and the null space of A. So, right, but I already reduced it all for you, so let's just use those matrices. So I'm working on a basis for col A. So let me just write this down here. Basis for col A is, okay. So if you remember from last class, you have to identify the pivot columns, right? So we can find the pivot columns here, here, and here, first, third, and fourth. So are those columns, those columns, but from A, the first, third, and fourth columns from the original A. Okay, so my basis for col A is going to be the first column from A, 1, 0, 3, -3. The third and fourth, 0, 1, 0, 3. And -1, 0, -2, 2. All right, does that make sense? Identify the pivot columns, grab them from the original matrix A. That gives you a basis for col A. All right, let's look at a basis for row A. Say what? Right, yeah, good. The column space of A transpose, yeah. Yeah. So let's go back. If we look at the notes, there was a handy little statement about how to find a basis for the row space, right? It's this right here. We use this theorem to find a basis for the row space of A. It says row reduce A to echelon form. So just echelon form, not fully row reduced echelon form. And use the non-zero rows to form a basis. So the non-zero rows of B, right? The non-zero rows of your echelon form, not A. So my non-zero rows of my echelon form are the first three. Yeah, 1, 2, and 3. So those will form a basis for the row space. Right, you use those numbers, not the original. I know. Do not use the original. Use the ones from B. Because row A, when you perform row operations, right? Row operations are just changing things, each row linearly, right? You can multiply by a constant, you can add things. Those are linear changes. But those change the rows linearly, but they change the columns in strange ways. So you can't say the columns aren't linear combinations of the originals. Yeah. But the rows are. No, it would not. The second one are just typically simpler, so we picked the simpler ones. Yep. Okay, so my basis for row A is going to be, here we go. I'm going to write them horizontally just so that we can kind of get used to seeing them that way, because your book does that sometimes. I do not mind. No. Math doesn't mind. No. Typically, when you write a vector horizontally, you use commas to separate the entries. Just like think of a point xy in R2. When you write it as a point, you write x comma y. When you write it as a vector, you write vertically xy. Okay, the last thing I want to find is a basis for null A. Okay, so anyone remember how we do that? Parametric vector form. Solve AX equals 0, put it in parametric vector form. I'm gonna grab the reduced echelon form here. No. Okay, so if this is my row reduced echelon form. So if it had been augmented with zeros, I would just have zeros over here, right? So my solutions to AX equals 0, I want to find all the solutions. So this is how I find the null space. And then the basis are the vectors from the parametric vector form. So this says x1 plus x2 equals 0. x3 equals, oops, x3 plus x7 equals 0. And x4 plus 4x5 plus 2x6 equals 0. right? And my pivots were x1, x2, sorry, x3 and x4. x1, x3, and x4 were my pivots. So I want to solve for my basic variables, for my pivot variables in terms of the free. Okay, so x1 is a pivot, so I'm going to solve for x1 here. So I have x1 is negative x2. Here, x3 is a pivot variable, so x3. Yep. Thank you. All right, and then x3 is negative x7. And then x4 is another pivot variable, so x solve for x4, and I get negative 4x5 minus 2x6. I'm kind of out of room here. Okay, so now my solution looks like a 7-vector x1, x2, x3, x5, x6, x7. Okay. So x1 is negative 2x2. x2 is a free variable, so I just put a 1 there. No, I just put an x2 there. Okay. Or right, I think when you're putting it in parametric vector form, having an x2 is a little easier to see what happens next. x3 is negative x7. Oops. x4 is negative 4x5 minus 2x6. x5, 6, and 7 are free, so I just write them in. And then I break this into parametric vector form. I use my free variables as parameters. So my free variables are x2, x5, x6, and x7. So I'm going to have 4 parameters here. x2, x5, x6, and x7. All right, and then in the first vector on x2, I have a negative 2 for the first entry, then a 1, and the rest are zeros. 1, 2, 3, 4, 5. Okay, so for x5, I have 0, 0, 0, and then negative 4, 1, 0, 0. x6, I have 0, 0, 0, negative 2, 0, 1, 0. And x7, 0, 0, negative 1, 0, 0, 0, 1. All right, so those 4 vectors for my parametric vector form, those form a basis for the null space of A. You take off the weights. Yeah, I'll write it all out. One, then negative 2, 1, 5 zeros.
So then we have the dimension for null space before, right?
Yes. Yep. All right, so we found bases for the column space of A, the row space of A, and the null space of A. Okay. Okay, how many vectors are in col A?
7.
Nope. Infinite. I tricked you, right? You all assumed I was talking about the basis of the column space of A, right? But the column space itself is the set of all linear combinations of the columns of A. There are infinite possibilities because you can put any weights. Yeah. Yep.
It would still be infinite for basis because you just have weights, right?
Nope. The basis is just those three vectors. Yeah. So there are three vectors in the basis for col A. All right, so let's come up with a vector in col A that is not in the basis, right? So it's not one of the vectors from the basis, and it's not one of the vectors that you gave in the original question. 10, 0, 30, negative 30. Sure, you can throw any weight on one of your basis vectors, and that will also be in the column space. Any linear combination of your basis vectors. 10, 0, 30, negative 30. That's a good one. Or any linear combinations of vectors in the basis. Okay, good. All right, how about an example of a vector in the row space of A that's not in the basis and not the one you gave in the original question? An example of in the row space. Yeah, any linear combination of the vectors from the row space. Yeah, so you just put a weight on the first one and zeros on the other two, and you get 2, 4, 0, negative 2, and then I lost it. Negative 8, negative 4, 0. Okay. An example of a vector in the null space of A, not in the basis, right? And not the one that we gave in part A. So the one we gave in part A was kind of like the cheap one because it's always in there, right? Yeah, so we look at our basis, you pick any linear combination of those four vectors, and that will be in null of A. So what'd you do? You put a weight of 2 on the first one, negative 4, 2, and then 5 zeros. Negative 4, 2, 1, 2, 3, 4, 5. Okay. Okay, so that's it for the demo. You got some activities. If you finish them early, I've got your take-home quiz that is going to be due Monday, right? So we're having a take-home quiz today instead of a regular quiz. So if you finish early, ask me for it. Don't leave without getting one because it's due Monday. If you don't get it, I don't care.